Hello everyone. Today we'll be starting the topic of linear search and binary search in an array. So first, let us consider linear search in an array. So as you all know, array is a data structure that consists of elements of same data type stored in a contiguous manner. Suppose let's take an example of an array. Suppose this is an array of integers. This is an array of integers. Let's name it as integer array. So as you know, the indexing of the arrays begins with 0. So this is the 0th index, this is first index, and so on. So let us consider the array of 10 elements. So the indexing will go from 0 to 9. Let's consider the elements in the array as 10, 20, 30, so on till 100. So as you can see, this is a sorted array. So what does linear search basically mean? Suppose I tell you to search or find the element 60 in an array. Suppose I tell you to find the element 60 in an array. So how will you approach this problem? So first you will compare the element 60 with 10. Is it equal to 10? No, we are finding 60. So we go to the next index. Is 20 equal to 60? No. So we go to the next index. So on. We keep on moving to the next index until we find the element 60. When we compare it with this element, we come to know that, okay, this is the element 60 and it is present at position 5. It is present at position 5. So this is how a linear search is carried. Suppose I want to search the element 100. So you, in this case, you will have to traverse from the first element to the last element. You'll start with 10. You'll search for 10, 20, 30, 40, 50, 60. Then you'll keep on searching till you go to the end of the array, and at the end of the array you'll find the element 100. So then you will return the position as 9. Okay, so this is one example where we have applied linear search of an array. So can you guys tell me what would be the time complexity of doing linear search in a sorted array? So in worst case, our algorithm will take O of n time. And why will it take O of n time? Because suppose we want to search last element, it may be last or second last. Then also you'll have to start from the first element, which is 10. And then you'll go from 10 to 20, 30. And so you'll have to traverse the whole array. Suppose the size of the array is 1 lakh elements. What will you do in that case? You'll have to traverse 1 lakh elements to go till the last element and then return the position. So this is something which is one of the disadvantage of doing linear search in a sorted array. In a sorted array, mind, like, just remember it, guys. We cannot apply any other technique other than the linear search in an unsorted array. But for sorted arrays, this is an exception. For sorted arrays, we have another technique which is known as binary search technique, which is known as a binary search technique. And it is a very, very efficient technique, which we will see in the coming part. So now we will go through the binary search technique. So what is binary search and how will we decrease the time complexity from O of n to less than O of n? Let's have a look. Suppose you can say, okay, so you can say, if I want to search the last element, what I can do is I can just start searching from the last element. Okay, like you will say start searching from the last index and go to first index. But in that case also, what happens is, suppose if I want to search first element, you never know what my first element is, what my middle element is, what my last element is. So as you do not have any idea about the array, you just know that the array is sorted. So 10 may be the first element, 10 may be the last element. Similarly, 100, it can be first element, it can be last element as well. So in this case, you cannot, even if you start from the beginning or from the end, the time complexity remains O of n in the worst case in linear search. So what is different in binary search? Let's have a look at how binary search is different. So binary search, and keep in mind, it's a very important point. Binary search cannot be applied to any other array other than the sorted ones. Binary search is applied only in sorted arrays. This is the most important part we have to remember. So this is the array of 10 elements. Let's name this array as array A. Okay, it is an integer type of array. Its array name is A. This is the 0th index and going on and until the 9th index. So how we do the searching in case of binary search? So the first thing we do is we find the middle element. Okay, how will the middle element help me? We'll have a look. We find the middle element. How can we find the middle element? The first element plus last divided by 2. The index of the first element plus the index of the last element by 2. Suppose if I take this as the left and I take this index as right. Then what I have to do is mid will be left index plus right index divided by 2. This will be the mid position. So in our case, what will be the mid position? See, the left index is 0 and the right index is 9. Okay, so the right index is 9 and the left index is 0. Let me show you with a red arrow. This is the left index and this is the right index. So what will we do? We will find the middle element, which will be 0 plus 9 by 2. So 9 by 2, which will give us 4. Okay, as it's an integer division, we'll get the answer as 4. So we get the 4th index. Okay, so you can ask, okay, what will I do with the 4th index? Suppose I want to search element 30. Suppose I want to search the element 30. So where are we finding the middle position? So what is the middle position? 4. 4 is the middle position. What is the element at the 4th position? The element at the 4th position is 50. The element at the 4th position is 50. Okay, so I can see one thing, that the element at any position, okay, suppose we consider this element 50, which is at the 4th position. All the elements, listen carefully, this is a very important point. All the elements to the left of 50 are less than 50. Okay, you can check 50, 40, 30, 20, 10. Why is it? It's but obvious because it's a sorted array. So as it is a sorted array, the elements to the left of any element will always be less than or equal to that element, and the elements to the right of the particular element will always be greater than that element. Okay, so all the elements to the left of 50 are less than 50 and to the right of 50 are more than 50. Okay, so you might ask, okay, we knew this, the array is sorted, so how is it helpful to us? It is very helpful to us. How? We'll have a look. So now we see the element which we have to find, that is element 30. Okay, we have to find the element 30. So we compare it at the element with the middle position. What is the middle position? The middle position is 4 and the element at the middle position is 50. So we compare 30 with 50. So is 30 equal to 50? No, obviously 30 is not equal to 50. Is 30 less than 50? Yes, 30 is less than 50. So what am I saying is, in this case, as 30 is less than 50, you do not have to search in the right part of 50. You just have to look in the left part of 50. And why is it? Because 30 is less than 50. So as the array is sorted, we cannot go towards the right part of the array, as all the elements to the right part of 50 will be greater than 50. So 30 will obviously be to the left part of 30. Okay, so you might say, okay, so half of the part is gone. So we are not looking at half of the array. We are considering only half of the array. That is 10, 20, 30, 40, 50. And what we'll do is, we'll continue this procedure. Now what will you do? I will do the same binary search in only this left half of the array. Again, I will find the middle element. And now what is the middle element? 0 is the left. And what will be my right now? My right will be this, right? Because I do not have to even look at 50 or elements greater than 50. So what is the area where I have to search now? From index 0 to index 3. So now my right will be index 3. So again, you will find the middle element, and then again, you will continue the same procedure throughout. Let's take an example and the things will be more clear as we go ahead. So what we'll do now is we'll do a dry run of the binary search program. Okay, we'll take a small array. Suppose, for example, we'll take an array of 6 elements. Okay, we'll take in sorted order 10, 25, 40, we can take 65, we can take 75. These are 5 elements, and we'll take off 8 elements. Okay, so this will be 80, 85, 97. Okay, so this is an array A. It goes from the index 0, and how many elements do we have here? So this is index 7. So we have 8 elements in total in this given array. So what will we do? We'll do a dry run of this program so that you understand the concept of binary search. Okay. So now, what is the first part? I told you, you need to find the middle element. You need to find the middle element. Suppose in this case, we are looking for, the question is that search for the element 85. Search for the element 85. So now what will we do? You will first step is to find the middle element. What is the middle element? Left plus right divided by 2. Left plus right divided by 2. And initially, what is our left index? Left index is 0. And what is the rightmost index? As you can see, it is 7. So right is 7. So now, considering this left and right, we will find the value of mid. So our mid will be left, which is 0 plus 7 by 2, which is 7 upon 2, which is 3. So our middle index is 3. Our middle index is 3. So now what will you do? I will compare the element. I will compare the element at the third index. What is the element at third index? 65. The element is 65. And what are we searching? We are searching 85, as you can see here. So is 85 equal to 65? No, that's the first case we'll be checking. We will be checking if the element is equal. So as the element is not equal, we'll go to the rightmost part. As the rightmost or leftmost part, it can be any. So now we have to search whether 85 is greater than 65 or less than 65. So as you know, 85 is greater than 65. So in that case, the 65 element and all the elements to the left of 65 will be ignored, because we will only search the right part of the array. We will only search the right part of the array, which is from index 4, which is from index 4 to index 7, which is from index 4 to index 7. So our new left, I'll just erase the left and right. We'll have to change it frequently. So our new left and new right will be, the left will be this 4 and right will be the same, because we have to search in the rightmost part of the array. So left will be 4, right will be 7. So we will find the mid again. This is the second iteration of mid. So during second iteration, the value of mid will be 4 plus 7 by 2, which is 11 by 2. What is 11 by 2? It's 5. So 11 by 2 is 5. So we search the element at the 5th position. The element at the 5th position is 80. And what are we looking for? 85. So first we'll compare. Is 80 equal to 85? No. But 85 is greater than 80. So now we will discard all the elements to the left of 80, because we are looking for an element greater than 80. So all these elements are ignored. So now our new left will be 85. Our new left will be 85, and the right will be the same. New left will be 6. I'm very sorry. The new left will be 6. And then the element at the 6th position is 85. So again, I'll update our left and I'll update the right. The right will be the same, which is 7. So what is our new left? Our new left is sixth index. So now mid will be 6 plus 7 by 2, which is 13 by 2, which is 13 by 2 is what? What is 13 by 2? Can you just tell me 13 by 2? 13 by 2 is again 6. So sixth position. Now we'll have a look at the sixth position. So what is the element at the sixth position? The element at the sixth position is 85. The element at the sixth position is 85. And it is the same element which we are looking for. We are looking at the element 85. So what will we return? We will return the current mid index. So what is the mid index? 6. So the element which we are looking for, which is 85, is present at the sixth position. This element is present at a sixth position. So how many iterations did we do? We just did 3 iterations. First, we found out the mid, that is 3. Then we found another mid which was 5. And then we found another mid which was the 6 and which gave us the required element. So in this case, in case of linear search, you would have to go from index 0 to 1 to 2 like that in a linear order going to index 6. But in this binary search algorithm, we have done the iterations only 3 times. Therefore, the time complexity of binary search is less than linear search for a sorted array. We will also have a look at the algorithm of binary search. I'll write the algorithm of binary search and explain how the procedure takes place. So in this function of binary search, you'll just pass an integer array, int array. You will pass the leftmost position, you will pass the rightmost position, and you will also pass the integer x, which you have to search. The integer x is the integer which you have to search. So now we'll be writing this function of binary search. So first thing, what is the first task you do? You calculate mid. You calculate value of mid, which is left plus right by 2. Left plus right by 2. This is the value of mid. So as I told you, after we calculate the value of mid, what's the first job we do? We compare the element at the mid index with the element we have to search for. If that is equal, we just return that index. As you can see, suppose the index here was 6, the mid index was 6. And the element at sixth position is the element which we are looking for. So we just return or print the index. So if the element at mid position, okay, if the array element at the mid position is equal to the element which we are looking for, that is x, then we just return the position of the element, that is mid. Okay, now there are 2 cases as I told you. If this is the first condition, which is if condition, then comes the second condition. Let's suppose, what will we do? Else if the element at the mid position is greater than the element we are searching for. It means we are looking for an element x which is smaller than the element present at the mid position. Then which array will you consider? Okay, let's take this example only. When first we got the mid as 65. Okay, so if the element is less than 65, which we are looking for, then we'll only consider the left part of the array. We'll only consider the left part of the array. So it gives us, we will call the binary search function. We will call the binary search function. We will pass the array, and what is the leftmost position will be the same because we are looking at the left part of the array. But the rightmost position will be the current position minus 1 because we will only be looking at the left side of the array and the element we are searching for. So this is what is called if the element is less than the element at the mid position. Then else, what is the condition remaining? That the element we are looking for is greater than the element at the mid position. In this case, we just do binary search on the right part of the middle element, which will be mid plus 1 array. Left will be the mid plus 1, right would be the n minus 1, it will be the x. So this is what we call a binary search algorithm. And there's a small condition which we have to look after. This is till when will we do this searching? So we will do this searching only till left is less than or equal to right. So once left passes the right position, we will stop searching for the element and return -1, stating that the element is not present in the given array. So this is the algorithm of binary search where we completely ignore half of the part of array again and again, and thus the time complexity, as we can see, I'll derive the recurrence relation first. Okay, so this is the main function which is called for the n elements, but then after that we are just considering half of the arrays here. We are just considering, I'll just do it in red pen. We will only consider this for half of the array, which is the leftmost part, and this function is being called for the rightmost part. But we need to be very careful that both of these would not be called at a time. Only one of them will be called, because either we will search in the left part or we will search in the right part. So what is the recurrence relation for binary search? The recurrence relation for binary search will be time complexity T of n will be T of n by 2, because we only search in the half part. Why it is not n by 2 plus n by 2, just 2n by 2? Because we either search in this left part of the array or we search in the right part of the array. We do not search in both the parts. So the time complexity will be T of n equal to T of n by 2 plus c. So if we solve this recurrence relation, we'll get the time complexity. We can solve it by Master's theorem or substitution method, and we'll get the time complexity as O of log n. Okay, and what was the time complexity of linear search? The time complexity of linear search was O of n, because we have to traverse all the elements of the array. So this is how in a sorted array using binary search, the time complexity can be brought down from O of n to O of log n. So this is how binary search, and there are many applications of binary search. So wherever the array is sorted and we need to search an element, or we need to find the frequencies of the element, we need to suppose calculate which is the element which is present more than n times, n by 2 times in an array, and all those problems in a sorted arrays can be solved easily using binary search, and that will reduce the time complexity from O of n to O of log n. That's it for today's session. Thank you.